All right, problem number 3. You draw 2 marbles at random from a jar that has 20 red marbles and 30 black marbles without replacement. Super important comment right there. So once you take a marble out of the jar, you are not putting it back in. What is the probability that both marbles are red? Okay, so I'm going to do probability that the first marble is red, probability that the second marble is red. Are these independent events? Are these independent events? Okay. They are not independent events. So I have to think of this more like a tree diagram. I can just write out my probabilities, but I have to kind of think of it like a tree. So if I think of this like a tree, I've got the option of red or not red. I know that technically here that'd be red or black, but I'm just thinking in terms of red or not. What's the chance that that first marble I pick out is a red marble? 20 out of 50. Am I putting that marble back? No. So assuming I did pick out a red marble the first time, what's the probability I pick out a red marble the second time? 19 out of 49. There's only 49 marbles left in the jar because I took one out and I didn't put it back. That's what that without replacement means. And we are assuming that I did get a red marble the first time. So 19 out of 49. To find the probability of the and of the intersection, we multiply along the branches. So I would multiply this with this to get the and, the intersection. So that's what I'm showing down here. I would multiply these two together. I need to grab a calculator for this because I certainly can't multiply these in my head. So 20 out of 50, that one's not too bad. That's 0.4. Times 19 over 49. On my yellow calculators, it gives it back to me as a fraction. That'd be 38 out of 245 in its reduced form. But when I change that into a decimal, it's 0.1551. So option A would be correct. Do you understand how we got there? Okay. Anytime I'm working with events that are not independent, I'm still going to be multiplying probabilities together, but I just have to figure out how that second probability is going to be different because they're not independent. Yes?
So we don't have to complete, like, the not black part? We don't have to complete the whole entire...
If I'm just asking a question like number 3, nope, you can just kind of think your way through it. In fact, on this one, I think when I did it on the answer key, I didn't even have the tree drawn. But the whole way that I know how to set up those fractions and which pieces I'm multiplying together is because I'm thinking of that tree diagram. Now, if I ask you to draw a tree diagram for me, you've got to fill in all the pieces. You have to fill in all the branches, and you have to fill in all of the ands at the end.
You don't have to show work.
Correct. For multiple choice, you do not have to show work. Number 6. So number 6 is not a multiple choice one, though. It's in the multiple choice section, but it's not a multiple choice question. If you buy one ticket in the provincial lottery, then the probability that you will win a prize is 0.11. All right, so I'm going to mark that so that I don't lose it. Given the nature of lotteries, the probability of winning is independent from month to month. You buy one ticket each month for 5 months. What is the probability that you lose all 5 months? Well, if the probability of win is 0.11, what is the probability that you lose? 0.89. 1 minus 0.11, so that'd be 0.89. When the events are independent, you don't have to say anything about what?
Like the chances change every month?
It says that they don't. It says that they're independent.
Okay.
All right, so I needed this 0.89, but that's not my final answer here. That's just the chance that I lose in any 1 month.
Yeah.
Yep. So when events are independent, you multiply to find the intersection. Technically, when my events aren't independent, I'm still multiplying, but I have to know how it's changing to find that intersection. Here, every single month, the probability of winning is exactly the same whether you won last month or not. So I've got 0.89, that's I lose the first month. Chance I lose the second month is another 0.89. Third month, fourth month, and fifth month. So I'm going to multiply all those together. That's my probability of lose for 5 months. Equals. So I've got 0.89 times itself 5 times, or 0.89 to the 5th power, rather than typing it in all those different times into my calculator. And when I do that, I get 0.5584. What is the probability that you will win at least one prize? Well, the probability of at least one would be 1 minus the probability that I win none. Because if I didn't win none, then that means I won something somewhere, right? We just found the probability that I won no prizes in 5 months. This would be 1 minus 0.5584. Should be 0.4416. So there's about a 56% chance that you don't win any prizes and about a 44% chance that you win at least 1 month out of there. You could win more, but it's not guaranteed.
Could you do it like 0.11 successful win times 0.8924?
So, no. And here's why. And we're going to learn about this in chapter 6. We only touched on the, like, what's the chance that I did do this at least once? So out of 5 months, come on. All of the different ways that this could happen. So there's the probability that I win every single month, right? So that'd be 0.11 to the 5th. Or I win the first month and I lose all the others. I lose the first month, I win, and then lose, lose, lose. Lose, lose, win, lose, lose. Do you see why it starts to get complicated? I have to write down all the ways that I could possibly win one or more. Like, I'm going to have to keep doing this over until I have everything except for this. So anytime I'm looking for at least one, I'm going to do 100% minus the probability of none because it's a whole lot less work. What else would you guys like to see? Yes? How do you do number 5? All right, if probability of A is equal to 0.24 and the probability of B is equal to 0.52, and A and B are independent, what is A or B? So the probability of A or B is equal to the probability of A. Sorry, that's not or, that's my and that I'm thinking of here. Probability of A plus probability of B minus the probability of A and B. This is how I find my or. If A and B are independent, then I can find that intersection. The probability of A and B, because they are independent, is equal to the probability of A times the probability of B. So let's go ahead and find that. The probability of A intersect B is equal to 0.24 times 0.52. 0.24 times 0.52 is 0.1248. So to find the probability of the union, the and, I have the probability of A, which is 0.24, plus the probability of B, which is 0.52, minus the probability of the intersection, which is 0.1248. When I add 0.24, 0.52 together, and I subtract out that intersection, I didn't realize I had that much more room. I end up with 0.6352, which is choice C. If I did not know the events were independent, I could not have answered this question. You have to know the events are independent because that's the only way we have with the information that's given to find the intersection that you have to subtract out. Yes. I don't believe so. I'll double check, I'll look at it again and let you know for sure, but I don't believe that the general addition rule is on that formula sheet. What else would you guys like to see? Or what other ones do you have questions about? Oh, I lied. General addition rule is on here. And also the given that, the probability of A and B divided by the probability of B, that's also on the formula sheet. It's on the front page. Yeah, those are the only two that they give you for probability. It's just those two there. They do not give you the rule where you multiply to find the intersection if they are independent, because if they're not independent, that's not what you do. If they're not independent, you have to know how the probability is changing. So for certain situations, I might not be able to find out what the intersection is unless I go out and I actually poll people and I can see it, touch it, feel it. If you're looking at a situation like drawing cards from a deck, I know exactly how that's going to change because I know how many cards there are, I know how many are being removed, and I know how that changes my probability. Yes. Number 11, absolutely. Find the conditional probability of A given B. So the probability of A given B. Again, this is one of the formulas that you get. That is the probability of A and B, the intersection, divided by the probability of B. Biggest thing I want you guys to remember about this is whatever this second piece is, whatever it is that's given, that's your denominator. The probability of that is your denominator. All right, an event A will occur with probability of 0.3, and event B will occur with probability of 0.7. There's my denominator. 0.7. The probability that at least A or B will occur is 0.8. Here they did not give me the and, they gave me the union, because that is my or. Do I have what I need for the numerator? No. You are given the general addition rule on the formula sheet, and that's what you're going to have to use to find what that numerator is. General addition rule says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection, the overlap, A and B. This is what we need for our numerator. So this is the piece that I'm interested in. I don't know that part, but I know all the other pieces. So I can sub in what I know. Probability of A or B is 0.8. The probability of A is 0.3. The probability of B is 0.7. Minus this piece that I'm looking for. The probability of A intersect B. So I'm going to add those two together, 0.3, 0.7. I get 1 minus the probability of A and B is equal to 0.8. Well, what would this have to be if I do 1 minus that and I get 0.8? 0.2. So 0.2 is my numerator. So left in fraction form, this would be 2/7. I don't even have it written in its decimal form. 0.2857. Leave it as a fraction or a decimal, I don't care. When you write it out in decimal form for probabilities, it's pretty standard to go out to 4 places on probabilities, because a lot of times we'll write these as percentages. And for a percentage, the first 2 places of the decimal would be my whole percent, and then I still want some decimal places after that. So it's pretty standard to go out to 4 places. Please don't just round to 2 places. Give me at least 3 if you're going to leave it in its decimal form. Do you have a question, Anthony? Anthony, did you have a question? Okay. Sorry, I thought I saw your hand go up. What else would you guys like to see? 12? And which one?
14.
12 and 14. Sounds good. We may conclude that events A and B are independent. Well, let's see. What is the probability of A? 0.3. What's the probability of A given B? 0.2857. Are those the same? Then they are not independent. We know that they are not independent because the probability of A does not equal the probability of A given B. Events A and B are mutually exclusive. What does mutually exclusive mean? Can't happen at the same time. So that means that the probability of A and B would have to be 0. Because if it's not 0, then you can have both of these happening at the same time. Are they mutually exclusive? Nope. Because the intersection is 0.2. Either A or B always occurs. Yes.
So for the first one,
Uh-huh.
since the probability of A is 0.3, when you round the
Nope.
oh,
Nope. No rounding. It's not exactly 100% identical. In order to be independent, they have to be exactly, not even one decimal place off, perfectly the same. Yes? Yes, I'm going to post this video on Canvas. All right, either A or B always occurs. What's the probability that A or B happens? 0.8. So A or B happens only 80% of the time. Is that certain? Is that guaranteed? Nope, so it's not that one either. Events A and B are complementary. And then we also have none of the above is correct, and then a typo. I don't know what that's all about. What does it mean by complementary? They add up to 100%, or we could say that the probability of B is equal to 1 minus the probability of A, or the way you said it, Brandon, is absolutely correct. Those individual probabilities add up to 100%. Is that true? Yes. That one is true, because we have 0.3 plus 0.7 equals 1. All right, 14 was the next one, right? Okay. Number 14, in your top dresser drawer are 6 blue socks, 10 gray socks, unpaired and mixed up. One dark morning, you pull 2 socks from the drawer without replacement, of course. You're going to pull one sock out, put it on. You're going to pull the other sock out, put it on. It's dark. You don't care if they match. What is the probability that the 2 socks match? Well, when you reach in the drawer, what can happen? What are the possibilities when you reach into that drawer? So how many socks total? 16 socks total. So we can pick out a blue sock. That would have a probability of 6 out of 16. Or we can grab a gray sock. That would have a probability 10 out of 16. Now we're going to follow both of these paths a little bit further, assuming that I draw a blue sock first. So given that the first sock ended up being blue, what's the chance that I draw a blue sock for the second one? 5 out of 15. That would be a match, right? If I pick a gray sock, would a blue and a gray be a match? Then I don't even care about that probability. I can fill it in if I want to, because I know that that would be 10 out of 15 because I grabbed a blue one the first time. But I don't need to put that in there because that's not what I'm interested in. Or I reach in, I grab a gray sock. If I reach in and I grab a gray sock the first time, what's the probability that when I reach in again, I get another gray sock? 9 out of 15. Again, I can fill in what the blue probability would be. If I grabbed gray the first time, then my probability for blue the second time would be 6 out of 15 because there's still 6 blue socks floating around in the drawer. This path right here leads to matching. And this path right here also leads to matching. Blue, blue, or gray, gray, right? What do I do with these fractions to get the probability of blue and blue? Multiply them. So I do 6 over 16 times 5 over 15. That gives me the probability of blue and blue. Or down here, I do 10 out of 16 times 9 out of 15. That's the probability of gray and gray. Is it possible that I have matching blue socks and matching gray socks that I put on my feet that morning? Can I do both? No. I either have one blue and one gray, or I've got a matching gray, or I've got a matching blue. I can't have blue and gray and gray. So these would be mutually exclusive events. If I want to know the probability of a match, I'm going to need to add those two probabilities together. So 6 out of 16 divided by 5 out of 15. I'm going to have to move my work over here. That would be 30 out of 240 plus 90 out of 240. That's blue and blue. Gray and gray. When I add those together, I get 120 out of 240, which would be a straight up 50%. How would this be different if the question said, what's the probability that you get mismatched socks? Like, what would I have done differently?
You would multiply 6, 16, and 10.
Yep, I would multiply 6 over 16 and 10 over 15. I would multiply 10 over 16 and 6 over 15, and then I would add those two together, because I either get blue and then gray, or I get gray and then blue. What else would you guys like to see?
Wait, you divided the 16, 6 over 16 and 5 over 15, or you multiplied it, right?
I multiplied these two together. Multiplied these two together, that's how I got the 30 over 240. I multiplied these two together, that's how I got the 90 over 240. And then I added those together, I got 120 over 240, which is 50%. Number 15, we should be able to answer this without any additional work. Since we're right here, are you guys okay if we go in and answer that? Using the example above, where in your dresser drawer there are 6 blue socks and 10 gray socks unpaired and mixed up. Given that the second sock picked is gray, what's the probability that the first sock was also gray? So the probability that first was gray, given that second was gray. Well, which of these would be an outcome of the second sock being gray? Gray, gray, or blue, gray, right? Oh, come on. So the probability that the second sock is gray would be the probability of gray and gray plus the probability of blue and gray over the probability of gray and gray. Well, we know the probability of gray and gray was 90 out of 240. So I'd have 90 out of 240 plus the probability that it's blue and then gray would be 60 out of 240, right? 6 over 16 times 10 over 15. This is how my other second, like my second sock is gray. That's the other way I could get a second sock that's gray. So I have 90 out of 240 over 150 out of 240. When my denominators match like that, I can just ignore them. So I get 90 over 150. That'd be 9 out of 15, or 3/5. So 60%. What else do you guys want to go over? Number 20? Absolutely. see if I can get that at the beginning. There we go. In a large high school, 24% of students are sophomores, 26% are juniors, and 30% are seniors. Of those students, 15% of sophomores, 25% of juniors, and 55% of seniors have parking passes. Suppose we select one student from this school at random and record which class they are in, as well as whether they have a parking pass. Find the probability that a student has a parking pass. Are freshmen allowed to get parking passes? Then I don't need to worry about the freshmen. There's a 0 probability that the freshmen have a parking pass. Thank you, Julia. All right, so we've got sophomores, juniors, and seniors. 0.24 probability of being a sophomore. 0.26 probability of being a junior. 0.30 probability of being a senior. Parking pass complement. Parking pass complement. Parking pass complement. I'm only interested in the ones that have parking passes, right? So I'm not even going to worry about the parking pass complement. Sophomores that have parking passes, what probability? 15%. So the probability that somebody is a sophomore and has a parking pass is 0.24 times 0.15. Probability of sophomore and parking pass. Percentage of juniors that have parking passes. 0.25. So 0.26 times 0.25 would give me the probability of juniors and parking pass. And what about seniors? 0.55. So 0.30 times 0.55 gives me the probability that somebody is a senior and has a parking pass. These three that I have written in orange, sophomore and parking pass, junior and parking pass, senior and parking pass, are those mutually exclusive? Could somebody be a sophomore and have a parking pass and also be a junior and have a parking pass? No. Are these mutually exclusive events? Then to find the probability of a parking pass, I'm going to take all the juniors with parking passes and I'm going to add it to all the sophomores. I'm going to add that to all the seniors. 0.24 times 0.15. Of course, I don't have that written down individually on my paper. I got 0.036. 0.26 times 0.25 is 0.065. And 0.30 times 0.55 gives me 0.165. So when I add those three together, I get 0.266. Suppose the person chosen does not have a parking pass. What's the probability that he or she is a junior? How would I write this probability statement? Because remember, you have to write probability statements for me. It's not enough to just have the answer like this one back here. To be correct, I need probability parking pass equals this. That would get you full points. Just having the 0.266 is not going to be enough. It's going to be close. You did all the heavy lifting. For part B, what does my probability statement look like? Yes, probability of junior given that they don't have a parking pass. So again, you get the given that rule on your formula sheet. So probability of junior and no parking pass over the probability of no parking pass. Do we have the probability of no parking pass? Can I find it because of what I just did in part A? Yep, that's going to be 1 minus 0.266. So my denominator here is 0.734. The probability of junior and no parking pass. Let's come back over here. This is one of the probabilities that we didn't calculate, but we can. I know the probability of being a junior is 0.26. What's the probability that that junior does not have a parking pass? 25% of the juniors have parking passes, right? So what percentage don't? 0.75. Because remember, every set of branches has to add up to what? 100%, or 1. So 0.26 times 0.75 is what I would have for my numerator. 0.26 times 0.75, 0.195 over 0.734. I get 0.266. Or if I took that out to 4 places, it's actually 2657, because it's not the 100% same answer as above. It just rounds to the same thing. Would this get me full points? Do I have my probability statement? As long as it's somewhere on there. You don't have to have like your final answer all boxed up nice. You have to show what you're finding the probability of, and I have to be able to follow your work to your final answer, but as long as you have that probability statement on there, you are good. All right, part C. Among the 40 seniors in the school's AP statistics class, that's astoundingly close to what we have this year, only 10 have a parking pass. The students are questioning whether the school is purposely not giving as many parking passes to seniors who take AP statistics. Below is a dot plot showing the number of seniors who have parking passes in 60 simulated classes of 40 seniors, assuming that students are selected randomly from a population in which 55% have parking passes from the school. Use the results of the simulation to determine if there's convincing evidence that the school is not purposely giving as many parking passes to seniors in AP statistics classes. So of the 40 seniors in the school's AP statistics classes, how many have parking passes? 10. Well, here's 10 on my dot plot. I'm going to count 10 and everything more extreme, so everything less than that. How many dots do we have over there? 9. Out of how many did we say were simulated? How many times did they run this simulation? 60. So 9 out of 60. What is that as a percentage or as a decimal? What'd you say? 3 over 20. 3 over 20 would be what? I got 0.15. Is that enough for me to say that I have convincing evidence that the school is cheating the AP Stat students? Why not? It's not 0.05 or less. Yeah, 5% or less. That's what's going to tip me off to say these kids are being treated unfairly. and the school is withholding parking passes from them. With our last minute, quick question. How would you actually run a simulation here? We're assuming that 55% of seniors have parking passes. How could you run a simulation that would give you a dot plot like this? Cards. So what I would probably do, and this is just me, I'm thinking on the fly because I didn't ask this question on here. I would probably have numbers 1 to 100. 55 of them would be students with parking passes, and the other 45 would be students without parking passes. And I would use a random number generator to pull 40 random numbers. And I would count how many of them had parking passes and put up a dot. And then I would do it again. I would have the random number generator pull 40 numbers again from that same 1 to 100. And I would do that, in this case, they did it 60 times, but you're going to do that many, 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 many times. We're starting with the assumption that this is true, that 55% of those students actually have parking passes. If you are trying to do a simulation, you need to find some kind of a chance device that you could use to model whatever the claimed probability is. In this case, it was 55%. And then you want to assign some of them to this condition and the remaining percentage to the other condition. I will post this video. I'm available on Canvas tonight. If you need any help, please, please, please send me messages.